Here we are once again. This is Physics 2A video lecture. Physics 2A video lecture 14. And last time we ended by looking at some heat engines. So today's discussion is all about heat engines. I showed you these demonstrations last time, and this time I'll just go through with the whole theory of it. And maybe I'll start with an announcement. So we're in the home stretch, definitely the final stretch of the semester. Keep taking really good notes and doing this homework. We have today's lecture, another one this week, and 2 more next week. Next week's lectures will primarily be review and a heads up for the exam, but we still have after today the theory of oscillations, which was this week's lab, but we're going to try to do a good treatment of the theory of oscillations. So there's still a lot to do, but we're doing fine. Good. So let's have a look here what we're talking about. Heat engines is the topic. And I'll review what it's all about. We know that there's the mechanical equivalent of heat that says that 1 calorie, so here let's write here, recall, mechanical equivalent of heat, 1 calorie equals 4,186 joules. This is a measure of changing the temperature of water, and this is mechanical. At this stage, once you know about the mechanical equivalent of heat, you can actually dispense with the calorie, but I'd like to keep it there just to remind us of its original thermal definition, okay, and content. But here we're just talking about work. That's how we learned about, kinetic energy, potential energy, and work. That's what we're talking about on this side. And what we want is to have a machine take this thermal energy and turn it into work, useful work. So for example, on the left side, we could be thinking gasoline. You just put it in a dish and burn it and you get a fire, okay? On the other hand, that fire is not going to drive you to work. If you put the gasoline in a mechanism, it can actually do some work for you. So that's the whole goal of this, and our entire civilization runs on these heat engines these days. Okay, we have some other energy sources, notably hydroelectric power, some nuclear power. Nuclear energy itself is a heat engine. So we have hydroelectric power and a little bit of solar and wind, okay, but those are small players. In the current time, we still have heat engines to do all of our work for us. Good, okay. So that was the whole reason for it. Oh, I could also remind us that we know that we can do work and get thermal energy with friction. So I like to write it this way. So work, friction turns, work into thermal energy, but what we want is this direction here. Okay. So the next thing was, after this motivation, was the example. And I gave 2 examples. The Christmas pyramid, which is a nice, very clear turbine situation, okay, with candles burning and this thing rotating. Okay, so it's called the Christmas pyramid. And we had the steam engine. I'm going to go into the steam engine in a little more detail this time. There was the boiler, there was the connecting rod to the wheel. So the steam engine, we had fire down here. Now, I'm going to expand on this a little bit in order to prepare for the general heat engine analysis. So yeah, a larger scale picture of the steam engine. Steam engine. Everybody saw that little model there functioning, very nice. But I'll pull it apart, and you can look these things up online and get some nicer images as well. So what we have here is a boiler I'll just write boiler. There is, and you know, we've got colors today, so we'll color our fire red. So we've got fire there coming off of some fuel. Okay, you saw that. So we're boiling the water in here and turning it into steam. So there's a certain amount of water in the boiler, okay, and that turns into steam. So if you just had this boiler with the water in it, you'd have steam under pressure, okay. So we take some of that steam, and I'll just indicate this with a pipe here, over to our cylinder, which has a piston inside, and this can actually stand to be expanded on, but we'll see. Piston connecting rod to a flywheel. So we have the cylinder. This here is the piston. The piston moves forward and back. Okay. This is the connecting rod. And this here is the flywheel. Okay. And what happens is we've got that steam here under high pressure, and it pushes this piston forward, and it turns this flywheel. Good, I'll just keep describing this and then I'll go into some of the math here. Okay, so the piston pushes forward here, and it's pushing against a resistance. So there's work. Force times displacement is work. And after it's done that work and this thing has spun a half a turn clockwise, we want to continue turning clockwise and push the piston back so the process can repeat itself. However, there's all that pressure in there, so you're not going to be able to push it back without doing work, and you're trying to get work from the machine. You're not trying to do work on the machine. So to get that work from the machine and keep getting work from the machine, a valve has to open on the return stroke, and then the steam inside here is pushed out. Then the valve closes, and then the steam pushes the thing forward again. And the flywheel has enough mass to just keep rotating and make sure the thing doesn't falter. And you get enough work out of this thing, you hook it up to a pulley or something, and then you can run a machine, okay? So you've got some machine over here. We had a little lamp post and a little light that glows in our little steam engine. So the valve releases steam. Okay. Good, so you can make clear how this process is working. The constant supply of steam under pressure pushes the piston forward, the wheel rotates. On the way back, the valve opens, and here I'll draw some steam being released. So every half cycle, steam's being released, the other half cycle, work is being done. Okay, so the work which is being done, so the work is force times displacement. That's how we learn about work originally, force times displacement. But in this chapter, there's another way of looking at it. This cylinder has a volume, and the volume here is changing. There's pressure inside, and the volume is changing as the piston gets pushed to the right here. So we can also write work is equal to pressure times change of volume. And I'm just going to do the dimensional analysis for you. So actually, let's write this in words first. Work dimensionally is pressure times volume. see what we have is a change of volume as this thing moves over to the right here. Okay, let's send this on. And there's a section on pressure and volume diagrams that we're not going to go into in detail, but this is a great place to talk about it briefly. So what is this pressure times volume? P delta V. Okay. What are the units of pressure? The units are force per area, force per area times volume, right? And if we're going to do the units of this, here, what if I do units of this, we'll have newtons per meter squared times meters cubed. Newtons per meter squared times meters cubed, and cancel the meter squared here, we end up with newtons times meters equals joules. Okay. So that's the significance of the pressure volume diagrams that you'll see in the section of your book, and that's where it's coming into play right here in our steam engine, among other things, but that's a good place to talk about it. Okay, so there's our steam engine. You can make an even nicer picture, maybe expand on the cylinder and the piston. Pressure times volume, very good. Okay, so what we're going to do next is the analysis of the steam engine. Now there's a really stereotypical heat engine diagram that I'm going to draw here and explain at some length. I can erase that, that was just dimensional analysis. So the analysis of the heat engine. This is a really useful, you'll find it everywhere, but this is a great analysis you want to take a close look at. So here's our heat engine system in this schematic diagram. I'm just going to draw these arrows first, and then I will explain them. So what we have here is what's called the, I'm going to label this TH. This is called the high temperature reservoir. What we're saying is we have some source of thermal energy at a high temperature. Okay. In our steam engine, it's the whole boiler set up here, right? It contains a lot of thermal energy, steam under high pressure. Okay. Now what this does is it gives off a certain amount of heat, a quantum of heat, of thermal energy at that high temperature, and it gives it off to the engine. Okay, and what does the engine do? It converts that energy into work. So there's the work that the engine kicks out for us, right? It's the rotating flywheel that we then hook up to a machine. So it kicks out this work, but what's going on here is utterly crucial. Namely, there always has to be some form of exhaust. So what we do is we say the exhaust or the waste heat is given off to the low temperature reservoir. So this is the low temperature reservoir. Low temperature reservoir. And this I'm going to write out is the work. This is why we did the whole thing, right? We want useful work from this. And this abstract schematic can be applied to most all heat engines. It can be applied to the Christmas pyramid. There, the high temperature reservoir is the hot air under the turbine. The low temperature air is the low temperature reservoir is the hot air above. Okay, so let me put that little Christmas pyramid here just to remind us. So there's our turbine. There are our candles. Okay. Okay, we've got some color here. Flame. And what did we have? What did we have? We had the convection current caused by the heated air spinning the turbine and doing useful work because it was carrying the wise men around in a circle. So yeah, what we have here is a higher temperature here and a lower temperature up here. So down lower, the high temperature, low temperature up above. And I'm bringing this up now because remember I did the chimney effect. By putting a chimney around this thing, I really separate these two. And the thing whirled like crazy. Okay, it was much, much more efficient when I was able to separate the high and the low temperature by having a chimney there. Okay, and this exhaust, this waste heat, as it's called waste heat. There's nothing wasteful about it. It's actually just part of the natural process. Up here, that would be the waste heat up there, okay? The exhaust that comes out, without which you cannot have a cycle. So you want a cycling heat engine, you have to have this. It's an integral part of the whole process. Okay, good. This is our schematic of the process, and the letters in here are the ones we're going to work with now. So what we have is energy at a higher temperature, energy at a lower temperature, we have work, and we have these higher and lower temperature reservoirs. Okay. Yeah, this is interesting. You can adopt this to many different types of energy power plant, heat engine power plant. But your car engine will also work in this fashion, although it's not as clearly pulled apart, because what you have is the combustion. I want to mention that briefly. In an automobile, the combustion is not here outside at the boiler, it's actually inside the cylinder itself, where a little bit of gasoline is injected and then a spark plug fires and the gasoline explodes. But the gasoline inside the cylinder that explodes is exploding at a given temperature, and there's a certain amount of energy in that amount of gasoline, so and so many joules per gram or something. And then the waste heat, of course, is the exhaust. Okay, so this also works for an internal combustion engine. Let's put that as a note here with these. There's external combustion. Okay, we've got external combustion, and that steam engine, versus internal combustion, and that's what you have in your car. Okay, internal combustion. So that's something to be aware of as well. Okay, what we're going to do though is continue with the analysis. How about I put this thing in a box here? I'm going to do an analysis of this scenario right here. And the question now is, how much work can we get out of a given amount of thermal energy? Which is, we want to know, how much work can we get out of a given amount of fuel, after all? Okay. And that's the question of the efficiency. Efficiency of the heat engine. In the development of these over the years from the, when was this, the 18th century, when they had the earliest heat engine, 19th century. So the development to higher and higher efficiencies made it necessary to do this analysis, because they started out being very inefficient. Okay, we're just glad to have a heat engine work at all. Nowadays, they're very, very dialed in. Okay, so the efficiency is the big question, and it's defined, letter E is equal to the work that you get out divided by thermal energy that you put in. Okay, so this is a dimensionless quantity, work divided by energy that you put in. And it's clear, since we know something about conservation of energy, that this number is less than or equal to 1. So E is less than or equal to 1 by energy conservation. But yeah, that's your basic definition of efficiency. Let's continue on. Okay, so now we get rid of a picture and just do the physics. Okay, so this is pretty abstract, and we're going to write down the conditions for an ideal heat engine. Okay, this efficiency, by the way, this is a very general definition, but let's look at what an ideal heat engine would entail. The ideal heat engine would have no losses at all due to friction. Okay, so the engine works perfectly smoothly, there's no friction, and the engine itself wouldn't get hot. There are no heat losses. The only heat losses are what comes out, we'll say for our purposes, what comes out of the tail of the exhaust pipe. That's where the heat losses occur, not on the engine itself. So the engine itself would be ideal, it would be insulated, no losses due to friction. So let me just write that down. Ideal heat engine, no losses due to friction. So that would be the first condition. The second condition would be the only heat loss is QC, and that is exhaust. Remember, we saw that QC is absolutely necessary for the functioning. Okay, so it's not, it's called waste heat, but it's not wasteful heat, it's just heat that goes out the exhaust. Okay, so the only heat loss is QC, there are no other losses due to friction. So now what we can do is define the ideal efficiency of the ideal engine. Okay, and that would be E, and I'm not going to give it another subscript. It would be the work divided by QH, but here, let me put this here first. So for the ideal engine, if there are no losses due to friction, we're talking about energy conservation. So let's write that down first. Okay, this was a little premature. So what does energy conservation tell us? Energy conservation tells us that the energy in is equal to the work plus the QC, the energy out. Okay, there are no losses anywhere else. There isn't a Q's of friction or a Q's of this or a Q's of that. It's either pure work or pure exhaust. So that is the law of energy conservation as applied to a heat engine right now, to an ideal heat engine. Now we do this efficiency. Now E is equal to W over QH. I'll go ahead and write it out, W over QH. But what is our W here? It's QH minus QC. Just bring that to the other side, divided by QH. And then by arithmetic, QH over QH is 1 minus QC over QH. Okay. So there's our efficiency. And I'm going to highlight it here. E sub ideal equals 1 minus QC divided by QH. Okay. So this itself just makes explicit what we had thought a minute ago. Namely, the efficiency can only be, or cannot be greater than 1, right? It's 1 minus something. And if there were no exhaust, no waste heat, it could be 1, but there has to be waste heat, okay? So the efficiency is always less than 1, even if it is an ideal engine, right? The perfect engine, the one the engineers are going to strive to accomplish. Okay, so that's an important point, this ideal efficiency, and this is due to energy conservation. You know, let me formulate this a little nicer. Now that we have this, I'm just going to keep that up there the whole time. So we've got the ideal heat engine. This is its ideal efficiency. So we'll just put this as a note. This expression star, E ideal is due to energy conservation. And another term for the energy conservation law is the first law of thermodynamics. If you look in the chapter, you'll see more discussion of that in context of the PV diagrams. But I'll just leave it right here. So energy conservation, i.e. the first law of thermodynamics. Let's just leave it at that. We've been talking about energy conservation all semester, and this is when you bring, we call it the first law of thermodynamics, when you finally bring heat into the system, or into the discussion. Good, so there's the ideal, E sub ideal, there we go. Okay, next, we're going to talk about the second law of thermodynamics. So next, apply the second law of thermodynamics. Now, I introduced that the other day. Who remembers what it was? I'll remind you. The second law of thermodynamics had to do with the entropy. That was entropy, total entropy of an isolated system is always increasing. The total entropy of an isolated system increases. And I'm going to apply the second law of thermodynamics to this drawing up here. But you know, I've drawn this board here. I'll go ahead and write this out first. So the second law of thermodynamics, the total entropy of an isolated system increases. So it increases in time. It doesn't decrease. And what did that refer to? That referred to disorder on the molecular level. So the disorder increases. And the other way to look at it was, and I'll just put this as a note, this was just an expression of this all-time simple cartoon, namely that the thermal energy flows from hot to cold. Okay, you should never forget this. That's the direction that the process unfolds, and that is a technical version of this law of nature, so to speak. Okay, so we're going to apply this, and that little bit of formalism I gave you, and you guys practiced it on the homework, we'll apply this little bit of formalism to this heat engine up here and get a great result out. Let me check to see how we're doing for time right now. Okay, we're doing fine. Okay, so the next task is to apply this second law to that idealized heat engine. And this is going to be pretty much what I did last time when I had this, energy going from hot to cold diagram, with a slight difference here. So for, so, no, not increase, let's write change of entropy for the heat engine. And here we go, we're going to have delta S total equals delta S for this upper part of the process, we'll label it H, then plus delta S for the work part of the process, that's the engine, plus delta S for the low temperature part of the process. In other words, there's the delta S for the energy leaving the high temperature reservoir and entering the engine. Okay, there's the delta S for the actual cycle that the engine goes through, and then there's the delta S for the exhaust, which goes from the engine to the low temperature reservoir. And these are easily written down. We'll make the Q's just be absolute values, quanta, so we'll have QH divided by TH. Remember, these temperatures are in Kelvin. Now the second one's interesting. I'm going to claim that change of entropy for a cycle of the engine is 0. That's because it's an ideal engine. No losses due to friction, no wear and tear. After it does a complete cycle, it's exactly where it started, so it hasn't become more disordered. Okay? That's why it's an ideal engine. So I'll write 0 here because ideal engine. And then plus QC over TC. So that's the total entropy change. And what we know about it is that it's going to be greater than or equal to 0. Okay. Total entropy change is greater than or equal to 0. That is the second law. Second law, exclamation point. So what that means is that I can set up an inequality here. If this right side is greater than or equal to 0, I can say that QC over TC must be greater than or equal to QH over TH. Mistake here. This was a quantum. I said this was an absolute value. So this gets the minus sign here. Got to do this discussion again briefly. So when the rule was when the energy leaves, we get a minus sign in the entropy change, and when it enters something, we get the plus sign. Yeah. So now when I bring this over to the other side, I had to catch that at some point, right? So we're getting QC over TC is greater than or equal to QH over TH. Okay. QC over TC greater than or equal to QH over TH, and I can therefore say QC divided by QH, and across, I'm going to divide this one there, is less than or equal to TC over TH. No, greater than. QC over QH can divide greater than or equal to TC divided by TH. Yeah, that's the inequality. You gotta watch out. Okay, so there we have a result. Gotta free up a little space here. Because now we're gonna take this expression star going to take this expression star, now E ideal, which is equal to 1 minus QC over QH, because QC over QH is greater than or equal to TC over TH, we can say this is less than or equal to 1 minus TC divided by TH. Okay. So this was just algebra and inequalities, okay, but a very important inequality because this thing simply came from the fact that energy flows from hot to cold originally. It's the second law. So now we have an inequality for the ideal efficiency is less than or equal to 1 minus TC over TH. So now we're not talking about the energy quanta, we're talking about the temperatures at which the heat engine operates. So having obtained this, I'll put up some exclamation points to convince you that it's important. Let's define something called the Carnot efficiency. Carnot was a French engineer who figured these things out. So the Carnot efficiency is this expression with an equal sign. So the Carnot efficiency E sub C is equal to 1 minus TC divided by TH. I'm going to put this in a box and discuss this. This is our grand result. Now I have to convince you that it's so important after we've done all this. Okay. So the ideal engine has an efficiency less than or equal to this Carnot efficiency. So this is an absolute limit. This itself is a law of nature. And it's independent of the workings of this heat engine. So any heat engine at all is going to have to obey this law right here. Okay? It's going to have to conform to this law. So this is the best conceivable efficiency, and so an engineer is going to work and try to achieve this efficiency, knowing that it cannot be exceeded, cannot be surpassed. Now, important is that we've been talking about Kelvin, the Kelvin scale for these T's, okay? These temperatures are Kelvin, because the Kelvin scale was used when we were talking about entropy. Okay. So that's the really important point. And yeah, we can just do some numerical examples of this to see what it means. Has a lot of applications actually. But yeah, we'll do some numerical applications, discuss this a bit, and then to end the whole discussion, I'm going to summarize what we need to know and give you a bunch of problems out of the text, chapter 12. And the summary is actually going to be pretty short. The summary will probably be this picture and then the formula is written here in a compact manner. Okay, so what about this Carnot efficiency? Example. All kinds of practical matters come into play here. So the example, first of all, we're going to imagine a steam engine that runs on boiling water, no particularly high pressure. So TH is 100 degrees Celsius, and it exhausts, the exhaust goes to room temperature because our steam engine's working in this room. So if you have TH is 100 degrees Celsius, TC is 20 degrees Celsius. First thing, of course, we have to convert this to Kelvin. So we have 100 plus 273, so we have 373 Kelvin. And here we have 293 Kelvin. So we want to calculate this little expression here for that. And I don't have my calculator with me, but we'll take this example up to here. And we'll get the Carnot efficiency will be 1 minus 293 over 373, which will be, you just rationalize the denominators, so we took a difference of 20 and 100. So this will be 80 over 373, and that's approximately 0.22. If memory serves, okay? So 20-some percent, 22%. Try it out on your calculator, something close to that. Okay. So 22% efficiency, so how much work did we get? For every 100 joules, we got 22 joules of work. So you might think, well, that's not very efficient, okay? But is it wasteful? Well, it's not wasteful. This is an ideal engine, and this just happens to be how much exhaust has to come out in order to get a certain amount of work. Okay, so now you guys may be a little disappointed and thinking a steam engine's not that efficient after all. And then you can go back here and say, well, what do we have to do in order to principally get very efficient heat engines? And it's very difficult to make TC much lower than the ambient temperature. Okay? So really, you want to make this denominator larger to make this ratio smaller. Okay? So you're going to have to run really hot engines. Okay? Really hot engines in order to increase your efficiency. And for example, you may have heard that diesel engines, powering your car, are more efficient in terms of miles per gallon. And it turns out that diesel engines work with a much higher compression, and with a higher compression, you have higher temperatures. So a diesel engine actually fulfills this condition of higher temperature, giving you better efficiency. Okay, so that's important. Now here's a couple of other points. One can go on and on with this. This low temperature, even if it's just room temperature, it is not a given, because you're exhausting the heat to the environment, but most of what you're burning is this exhaust, and what can happen is you're unable to exhaust it rapidly enough, and in that case, your engine's actually going to build up heat. It'll become heat soaked, and then effectively this TC goes up. It's effectively no longer that low, and then your efficiency goes down. So it becomes very important to draw away this waste heat as efficiently as possible, as effectively as possible. So in power plants, let me draw a little picture of a power plant, so you know what we're talking about. So maybe you've seen a power plant before, and there's some building here, and there's some kind of smokestack, okay? And, maybe there's a couple of them, fine. But over here, there's some connection. There are these enormous cooling towers. Okay, who's seen this kind of thing? And the cooling tower is giving off enormous amounts of steam. It's just vapor. There's no exhaust coming out of the cooling tower. Here, I'll draw something for us. Right, there are huge clouds coming out of this thing. And the reason for this enormous cooling tower is just to draw the heat off of the system. Okay? They use water, they drip water down, converts to steam, it draws the heat off of this. Otherwise, the machine's not going to, it's not going to operate efficiently. And what's feeding these things is maybe an infinite loop of train cars that are just dumping fuel, dumping coal into this power plant the whole time. Okay. So yeah, these are gigantic operations that run our whole civilization. They're based on heat engines. A nuclear power plant will not be burning coal, but it will have a different source of heat, but it will use a normal steam turbine engine, and this half of the nuclear power plant will also just use a cooling tower. So instead of this thing, you've seen the pictures of something with a containment dome, right? And that's the power plant. It's much smaller, these gigantic cooling towers, and there could be more of them. There could be a whole string of them. They're just getting rid of the heat. Okay, so enough of that. That's a subject you can be interested in and look into. I am going to summarize the whole thing here and give you guys some homework problems. So we're always referring to this schematic. So that's going to stay up here. And what all these formulas I'm just going to repeat, repeat small compact form, and then we'll set up a couple problems. So we have the heat engine here, we have the efficiency, we have the efficiency in this case, in this form, where QH equals W plus QC. So we have the definition of efficiency, we have the first law of thermodynamics, which is just energy conservation. That gives us the second definition of efficiency. I'll kind of number these. And then we have the Carnot efficiency, 1 minus TC divided by TH, where T is in Kelvin. Okay. But it's fair for me to state the temperature differences, or temperatures in Celsius, because those are common ones. You have to remember to convert them. Okay, anything else? Yeah, these are basically your formulas. 1, 2, 3, 4 for the whole heat engine discussion. Let's put here. Then power P equals W over T. This one is also fair to add in the discussion, because a lot of problems about power plants are going to be giving you some performance in watts, or some certain amount of power, kilowatts and so forth. Okay, so this is very important. You have to remember watts, joules, seconds. Okay, work over time, and work is power times time, etc. Yeah, that's just another formulation of that one. Okay, so that summarizes it. This here you should really understand what's up on this upper board here after all this discussion. Okay, let's look at some homework problems. So none of these problems that I'm going to give are difficult. They all just involve these formulas, and if you have this flow chart, these formulas, you should be able to figure anything out. So let's see what we have here. Homework. And I'll put one, even possibly two of these, more likely one, right, on the final exam. But I'm going to make them all pretty similar. So we're looking here, chapter 12, and the section on heat engines and the second law of thermodynamics. Yeah, we're just going to do a bunch of very basic ones. So 33 is what I just did on the board with the steam example. I think I'm just going to give a whole string of these here. They're all very basic. So 33, 34. So 33, 34, 35, 36, and 37. Let's see if there's one that's particularly interesting. And 39. Yeah, this one explicitly makes use of their. Yeah, these are basic, but once you do those, you'll have a good grasp. Okay, before we stop this, principally, we don't need to know more than what we have here to do the following type of energy conversion. So I'll write here, finally, energy conversions. I've probably discussed this before, When you pay your bill, your energy bill, it's in kilowatts, kilowatt hours actually. So what is a kilowatt hour? Okay, kilowatt hour, kilo stands for 1,000, watt stands for joules per second, and hour stands for 60 minutes times 60 seconds, or 3,600 seconds. The seconds cancel, so a kilowatt hour is it's 3.6 times 10 to the 6 joules. Okay. So it's just a number, you use scientific notation. So you can figure out how many kilowatt hours you pay, you can figure out how many kilowatt hours a whole city pays, a whole nation pays or uses. Okay, so that's just an energy quantum. On the other hand, you could imagine a big block of coal or a big barrel of oil. How much does it have? How big does this block have to be? How much do you have to supply this many kilowatt hours? Okay. These are just energy conversions, and then you can figure out how big of a hole in the ground would it take, to supply yourself, the city, the state, etc. So all of these, large-scale calculations are really within your grasp, and then you know something about the efficiencies, you can narrow it down. Okay, so I just want to bring out the fact that with this knowledge we have here, we can really understand energy usage on any scale. Small home scale to grand scale, because it's just energy conversions, and otherwise they're just algebraic expressions. Okay, so take a look at these problems. They're all very basic, making use of that there. And that will end our chapter 12 work. We have one more chapter to go through now on oscillations. That will be next time. So just keep taking your good notes, and we'll see you next time.